Hello and welcome, and today we're going to talk about an electronic configuration. But what is an electronic configuration? Well, the electronic configuration of an atom shows the number of electrons in each sub-level or subshell in each energy level or quantum shell of the atom. We have to know that it's very related with periodic table, and we can state the electronic configuration of any atom or ion according to their position in the periodic table. So hydrogen only has one electron, so it has a 1s1 electronic configuration. This one talks about the quantum shell in which the subshell is in, and this the number of electrons in that subshell. Secondly, we have helium, which is 1s2. Again, first quantum shell, 2 electrons. Then we go to lithium, which is 1s2, 2s1. Then we go to oxygen, which is 1s2, 2s2, 2p, 1, 2, 3, 4. Then we go to magnesium, which is 1s2, 2s2, 2p6, and 3s2. This is very easy, but sometimes it gets more difficult because not all of the subshells escalate in a pattern of energy. So, for example, we have first the 4s, and the 3d has a higher energy than the 4s, although it's in a lower quantum shell. So we would start first with the 4s and then fill the 3d, although there are some exceptions. So let's get an example. Scandium is 1s2, 2s2, 2p6, 3s2, 3p6, and finally we get to the 4s2. So remember, it's first 4s around the 3d and then 3d1. Remember that up to 10 electrons can fill in a d subshell. Although there are some exceptions, of course. With copper, for example, or with chromium, you fill one electron, so one electron from the 4s subshell moves to the 3d. So the following electronic configurations of copper and chromium. Copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d10. Later on, we'll talk about why these exceptions occur, which relate to ionization energy, stability, and so on. Chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. Okay, so now we have to talk about the different laws that occur when we fill in electrons in energy levels. First is Hund's rule, which basically states that electrons will occupy the orbital singly before pairing up. So we have p orbital, we have px, py, and pz. First of all, they'll fill in one from each orbital, and then they'll start pairing up. This is known as Hund's rule. Then we have the Pauli exclusion principle, which states that two electrons cannot occupy the same orbital unless they have opposite spins. Electron spin is usually shown by the use of upwards and downwards arrows. So this is what I showed here. That's what we have to know, that in each orbital the arrows are basically opposite because their spins are opposite. We also have to know about box notation, which is basically another way of writing electronic configuration. So for example, for oxygen, I'll show it now. We have the 1s, the 2s, 2px, 2py, 2pz. The 1s is full, 2s is also full, and then we have 4 electrons in the p subshell. So first of all we go like this before pairing up. That's untrue, and then we fill in the first orbital with an opposite spin. Pauli exclusion principle. So that's basically it, but I just wanted to talk a bit more about the periodic table and how it works. So the way you do it is basically these 2 columns are for the S energy levels, this for the P, and this corresponds to the D's. So for example, when we get, let's say for example, sodium, we go 2s, oh this is by the way S, because it's supposed to be there. Then we get 2s2, then we get 2p6, 1, 2, 3, 4, 5, 6. Second row, so second quantum shell. 3, third quantum shell. S subshell, 1 electron. So that's basically it. I hope this has been useful and you have learned something new. Bye!